So the kinds of technologies that we use to build blockchain protocols have changed a lot over the last 10 years, right? So when Bitcoin was created back in 2009, it actually used very simple forms of cryptography, right? The only kind of cryptography that you see in the Bitcoin protocol, you had hashes and you had elliptic curve ECDSA signatures. And you had proof of work, and proof of work is just another way of using hashes. If you look at the kinds of technologies that are being used to build protocols in the 2020s, you start to see this much more complex set of techniques that have really only come into existence over the last 10 years, right? Now, a lot of these things, they definitely existed for a long time, right? So we've technically had ZK snarks ever since the PCP theorem, which was several decades old. We've had fully homomorphic encryption ever since Craig Gentry's discovery in 2009. We've had garbled circuits, which are a form of two-party computation for decades. But there is a difference between these technologies existing in theory and these technologies existing in practice, right? So in theory, these technologies have existed for a long time, but in practice, there has been this large efficiency barrier between what you can do inside of an academic paper and what kinds of things you can actually make practical and actually put inside of an application. And I actually think it is the blockchain space itself that has a lot to take credit for in actually bringing the resources to take a lot of these technologies and actually bring them to the stage where you actually can use them inside of regular applications, right? The difference between ZK snarks as they were in 2010, ZK snarks as they were in 2016 when they were first used inside of the Zcash protocol, which launched in December of that year, and ZK snarks as they exist today is just massive, right? So a lot of these newer forms of cryptography, these are things that have gone from being something almost nobody knew about to being a niche interest, to being mainstream, to almost being defaults today, are things that have changed and things that have improved massively over the last decade. This includes a lot of different things, and the protocols that we have today are increasingly relying on all of these technologies, right? Blockchains built in the 2010s were built with the assumption in mind that hashes and signatures were all you have. Blockchain protocols that are built in the 2020s are being built with all of these things natively, being considered as key components from day one. So ZK snarks are the first major thing here, right? So ZK snarks are a technology that allows you to prove that you ran a computation and that you got some output from the computation. And you can do this in such a way that the proof is much faster to verify than to run the computation yourself. And you can also, that the proof can be verified while hiding a lot of the information from the original input. So ZK snarks are extremely useful in privacy, and they are extremely useful in scalability. Now, what do blockchains do, right? Blockchains give you a lot of benefits. They give you openness, they give you permissionless access, they give you global verifiability, but all of this comes at the expense of two very big things. One is privacy, the other is security. ZK snarks give you back privacy and give you back security. So in 2016, we saw the Zcash protocol. Then increasingly, we've started to see more and more things inside of the Ethereum ecosystem. And today, pretty much like everything is starting to be built on ZK snarks. Multi-party computation and fully homomorphic encryption. So these are things that people hear about less than ZK snarks today, but there are certain kinds of things that you cannot do with ZK snarks. So privacy preserving computation running on people's private data. Voting is actually one big use case where you can get a certain level of properties with voting with ZK snarks, but if you want to get really the best properties, then MPC and FHE are things that you have to use. A lot of crypto AI applications also end up using MPC and FHE, and these are both primitives that have been improving rapidly in efficiency over the last decade. BLS aggregation. So BLS aggregation is this interesting technique that basically lets you take a whole bunch of signatures from a whole bunch of different participants, maybe potentially tens of thousands of participants, and then verify that combined signature as quickly as you can verify one single signature. This is powerful. The BLS aggregation is actually a technology that is at the core of Ethereum's modern proof-of-stake consensus, right? So if you look at proof-of-stake consensus that was built before BLS aggregation, a lot of the time, the algorithms could often only support maybe a few hundred validators. In Ethereum, Ethereum currently has about 30,000 validators that are submitting a signature every single slot, right, every 12 seconds. And this is only possible because of this new form of cryptography that has really only been optimized well enough to be used over the last 5 to 10 years. So a lot of things are being, a lot of these new technologies, they're becoming much stronger. They're becoming much stronger very quickly. And the protocols of today are heavily using all of these technologies, right? We've really had this big shift from special purpose cryptography to general purpose cryptography. From cryptography where to create a new protocol, you have to understand how the cryptography works yourself. You have to create a special purpose algorithm for a special purpose application, to a much more general purpose world where to create an application that uses the things that I talked about in the last 5 minutes, you do not even need to be a cryptographer. You can just write a piece of code, you write a piece of code in CIRCOM, and then CIRCOM compiles it into a prover and a verifier, and you have a Zstars application. So what are the challenges here, right? Basically, the question is, we've gone very far over the last 10 years. What is left, right? What is the distance between where we are with these technologies today and the theoretical ideal? And this, I think, is the key area where like researchers and people from the academic community can really have a lot of room to help here. And I think the two big problems right now are basically, one is efficiency and the other is safety, right? Now, there is a third one, which is, you could say, expanding functionality, right? So one thing that we don't really have yet, for example, is indistinguishability obfuscation. And if we could have an algorithm for that that's viable, then it would be even more amazing. But actually, I think improving the efficiency and improving the safety of the stuff that we have today, I would consider it even more important. So let's talk about efficiency, right? And let's talk about one specific example, which is the Ethereum blockchain. So in Ethereum, the slot time is 12 seconds, right? The average time between one block and the next block is 12 seconds. The normal block verification time, so this is the time that it takes for an Ethereum node to verify a block, is about 400 milliseconds. The time that it takes to zk-snark prove an average Ethereum block right now is about 20 minutes. This is improving quickly. 2 years ago, this was 5 hours. Now it's 20 minutes. Now, 20 minutes is an average, right? There's still worst case situations. So for example, if you have an Ethereum block where that entire Ethereum block is just doing Keccak hash computations, it's going to take longer than 20 minutes to prove. But we're still a lot further along than we were 2 years ago. Now, what is the goal? The goal is to have real-time proving, right? The goal is that when a block is created, that you get a proof of the block before the next block gets created, right? And when we have real-time proving, what do we have? We basically have a world where every single Ethereum user in the world can very easily become a fully verifying user of the Ethereum protocol, right? So who here has an Ethereum wallet? Who here is running an Ethereum node, verifying the Ethereum chain? Good. See, a lot of people, right? But fewer people, right? So I have an Ethereum node. I actually have a ref archive node. It takes 2 terabytes, right? So you could do it, but it's inefficient. What if we could get to a world where every single Ethereum wallet, including browser wallets, including mobile wallets, including wallets that are smart contracts of other chains, are actually fully verifying the Ethereum consensus rules, and so they're not actually trusting Infura, they're not even trusting Ethereum proof-of-stake validators, they actually are directly validating the rules and directly making sure that Ethereum blocks are correct. How do we do this? With Zstars. But for this to actually work, ZK Snark proving needs to be real time. There needs to be a way for an Ethereum block to be proven probably within 5 seconds. So the question is, can we get there? Now, MPC and FHE also have similar issues. So one powerful use case of MPC and FHE, as I mentioned before, is voting, right? And it's actually starting to be used. There was an Ethereum event in Vietnam about 3 weeks ago, and at that event, they were actually using Macy, which was one of these cryptographic secure voting systems, to actually do the voting inside of for projects in their hackathon. Now, the problem with Macy in its current form is that it relies on one central server for some of its security properties. Can we decentralize that trust assumption? We can, but it requires MPC and FHE. Now, the problem is these protocols need to be efficient, right? These protocols have high overhead. You have FHE on top of a snark, on top of a signature, and this carries a lot of inefficiency. And for these protocols to be things that regular people use by default, it cannot be a thing where it costs like $5 of computation to prove every vote, right? It has to be a thing where it happens very quickly and it can happen even for large numbers of voters in real time. So how do we get there? For ZK Snarks, I think there's 3 big categories of efficiency improvements. One of them is parallelization and aggregation, right? So if you imagine an Ethereum block, verifying an Ethereum block requires a maximum of about 10 million computational steps. You take each of these computational steps and you separately make a proof of it. Then you do proof aggregation. You take the first 2 proofs, you make a proof of those proofs. You take the next 2 proofs, you make a proof of those proofs. You take the 2 proofs after that, you make a proof of those proofs. You take your first 2 proofs of proofs, you make a proof of the proofs of the proofs. And you have a tree, and after about 20 steps of the tree, you have one big proof that represents the correctness of the entire block. This is something that can be done today with present technology, and it could prove the correctness of an Ethereum block within 5 seconds. What's the problem? Basically, it requires a huge amount of parallel computation, right? It requires 10 million provers. So can we optimize this, right? Can we optimize parallelization? Can we optimize aggregate proofs? And the answer is yes, right? And there's a lot of theoretical ideas for how to do this, but this is something that really needs to be turned into something practical, right? And this is a problem that combines improvements in algorithms with these very low-level improvements in hardware design. Efficiency improvements and ASICs, right? So ASICs are also really important. So we've all seen here what ASICs can do to Bitcoin mining, right? Who here remembers back in 2013 when ASICs started coming online as miners for the first time, and we saw how quickly the Bitcoin hash power went up? Who remembers this? Okay, it's ASICs are very powerful, right? An ASIC was able to do basically about 100 times more hashing than a GPU for the same hardware cost and the same electricity cost. And so the question is, can we get this exact same benefit for snark proving? And I think the answer is we should be able to, right? And so there are a lot, more and more companies that have been starting to actually build ASICs specifically to prove ZK snarks. Could be ZK EVMs, but actually it should be pretty general purpose. You should be able to make a snark ASIC to prove any kind of computation. And by doing that, can we get from 20 minutes to 5 seconds? Finally, efficiency improvements, right? So making better ZK snark algorithms. So we have GKR, we have lookup tables, we have 64-bit snarks, we have starks, we have 32-bit starks, all kinds of different ideas. Can we improve the efficiency of the snarking algorithms more? And can we create more snark-friendly hash functions, more snark-friendly signature algorithms? So a lot of ideas here, and I highly encourage people to do much more to work on these ideas. Main safety problem, bugs, right? So bugs are, I think, one of the biggest things that people really don't talk about, but they're incredibly important, right? Basically, we have all of these amazing forms of cryptography, but people are not going to trust them if people are afraid that there is some kind of flaw in the circuit, right? ZK EVM circuits, they have 7,000 lines of code, and that's if they're done very efficiently. On average, code has 15 to 50 bugs every 1,000 lines of code. In Ethereum, we try hard, and it's less than 15 per 1,000 lines, but it's more than 0, right? And if you have these systems that are holding billions of dollars of people's assets, then if you have a bug in one of them, then it doesn't matter how advanced the cryptography is, the money's going to get lost. And so the question is, well, what can we do to really take existing cryptography and reduce the amount of errors inside of it? So today, the basic technique that is used here is security councils, right? Basically, you just have some group of people. In Arbitrum, for example, it's 6 out of 8. Or actually, no, I think they go even higher now. I think 9 out of 12. And there's a group of people where if most of them, more than 75% of them agree that there is a bug, then they can override whatever the proof system says. So it is fairly centralized, but this is the best that we have today. In the near future, we have multi-provers, right? So over here, you have a diagram from Tycho, which is one of the Ethereum-based rollups. And the idea here is that you have multiple proof systems. And so the theory is that you use redundancy to reduce the risk of a bug in any one of them, right? You have 3 proving systems, and if there is a bug in one of them, then hopefully the other 2 will not have a bug in the exact same place. Finally, I think one interesting further future thing to look into is using AI tools, potentially using new tools to do formal verification, right? To actually mathematically prove that something like a ZK EVM does not have bugs in it, right? Basically, can you actually prove that for example, a ZK EVM implementation is verifying the exact same function as the Ethereum implementation in Geth, for example, right? Can you prove that they only have one output for any possible input? And if you can try to actually prove those things, then maybe we might actually be able to get to a world where we can actually have bug-free ZK EVMs at some point in the future. Now, this is crazy, right? And no one has made a program of this level of complexity bug-free before. But in 2019, no one thought that it was possible to use AI to make really beautiful pictures, right? And so today, we just see just how much progress we've seen AI do. And the question is, can we try to turn similar tools toward the task of actually automatically generating mathematical proofs for complex statements over programs that stretch across many thousands of lines of code? I think this is an interesting open challenge for people to look at. Efficiency and signature aggregation, right? So today, Ethereum has 30,000 signatures per slot, and the requirements to run a node are pretty high, right? So I have an Ethereum node on my laptop, and it runs, but it's not a cheap laptop, right? And I did have to go and upgrade the hard drive myself. Desired goals are, in Ethereum, we want to support as many validators as possible. We want proof of stake to be as democratized as possible for people to be able to directly participate in validating at any scale. We want the requirements to run an Ethereum node to be very low, to be very easy to use. And we want the Ethereum protocol to be maximally simple. So what are the theoretical limits here, right? The theoretical limits are there needs to be 1 bit per participant per slot of all the data, because you have to broadcast the information of who participated in signing and who did not, right? This is the most fundamental limit. Above this, there are no other limits, right? Computation, no lower bound. You can do proof aggregation, you can do recursive proof trees, you can do all kinds of signature aggregation. You can use Starks, you can use lattices, you can use 32-bit Starks, all kinds of different techniques. And the question is, just how far can we optimize signature aggregation, right? Peer-to-peer safety. So people don't think enough about peer-to-peer networks. This is something I want to really emphasize, right? I think in the crypto space, there is often too much of a tendency to create fancy constructions on top of a peer-to-peer network and then just assume that the peer-to-peer network works. There's a lot of demons hiding in here, right? There's And I think those daemons are about to become more complicated. The way that peer-to-peer networks work in Bitcoin and the way that they work in Bitcoin in the 2010s is that every node sees everything, right? And there are definitely attacks that you can do. There's eclipse attacks, there's denial of service attacks, there's all kinds of attacks. But when you have a very simple network and the only task of the network is to make sure that everyone gets everything, then the problem is still fairly simple. The problem is that as Ethereum scales, the peer-to-peer networking is becoming more complex. The Ethereum peer-to-peer in today already has 64 subnets, right? In order to do signature aggregation, in order to process 30,000 signatures per slot as we do today, we have a peer-to-peer network that's split into 64 different subnetworks where each node is only part of one or a few of those networks. In data availability sampling, this is the technology that Ethereum is using to give data space for blobs, so to give scalability to layer 2 projects and allow rollups to have very low fees. This also depends on a more complicated peer-to-peer architecture. So this over here, you have a diagram of PeerDAS. In PeerDAS, every node only downloads 1/8 of all the data. And so the question is like, well, can you actually make a network like this safe? Can you make it provably safe? Can you push the guarantees up as much as possible, right? How can we preserve and how can we improve the safety of the peer-to-peer networks that Ethereum depends on? So conclusions, right? Basically, I think at this point, the thing that we need to be looking at is we need protocols that achieve the limits of what you can do with cryptography, right? We've gotten to the point where our cryptography is much stronger than it was 1 decade ago, but it can be even stronger, right? And it's at the point where I think we really need to start looking at what is the ceiling and how do we actually reach the ceiling. And there's 2 frontiers here that are equally important. One of those frontiers is to continue improving efficiency, right? We want real-time proving of everything. We want to see a world where every message that gets passed around in a decentralized protocol has a ZK snark attached by default, proving that that message and everything that the message depends on followed the rules of the protocol. How do we actually get there? How can we improve efficiency enough to make that happen? And then frontier number 2 is to improve safety, right? Basically reduce the chance that something goes wrong and get us to a world where the actual technology underlying these protocols can be something that's very robust and very trusted and people can depend on as much as possible, right? While these projects have bugs, people are not going to rely on the cryptography and people will continue relying on people. But as we've seen with many times over, multisigs can get hacked, right? There have been many instances where you had these so-called layer 2 projects, and the coins inside of those layer 2 projects, they're actually controlled by a multisig, and somehow like 5 out of 9 got hacked at the same time, and a lot of money got lost, right? If we want to move beyond that world, then we need to trust, like actually be able to use the technology and actually cryptographically enforce that the rules are followed instead of trusting a small group of people to making sure that happens. But for that to actually be possible, the code needs to actually be trustworthy, right? And so the question is, can we make the code trustworthy? Can we make the networks trustworthy? Can we make the economics of these protocols trustworthy? And I think these are the core challenges that I hope we can all continue working together to improve on. Thank you.